So what we want to be able to do by the end of today's lesson is to describe or illustrate the relationship between sets using either set notation or Venn diagrams. Now, we've talked a little bit about sets before when we were listing out the possibilities of a set of events or a set of outcomes, and we said things like if you wanted to list out the set of, I don't know, fruit or something like that, you could have a set called fruit. You had these curly brackets to indicate that what was inside here were the elements of the set, and you could put things like I don't know, apple, pear are elements in the set of fruit that you have. As we're going along through Unit 2, we are going to use some specific symbols and some definitions, sort of mathematical terminology for talking about sets. We are going to talk about a set called S, capital S, and often the names of sets are bolded. This is what we're going to refer to as the universal set. What makes it universal? Well, it's got everything in it. Now, when we say everything, it doesn't mean sort of everything in the entire universe. It means everything in the context of our question. Okay, so we could have a question about food. The universal set would contain all the different types of food. Okay, and then we might have fruit as a subset of food. The universal set, if we were talking about food, wouldn't contain bicycles or something like that. So it depends on the context of the question, what is in that universal set. And then we have this little symbol here that looks like an N. Okay, this is an operator that we use when we're comparing two sets. Okay, this means intersection. And if you've done computers and you've done Boolean logic, this is often written as AND. What this means is when we have two sets, we are interested in the elements that are in one set and in the other set. So the elements have to be in both sets. So we're looking at elements common to both sets. And it always goes between two sets. The next one that looks like a U here is referred to as the union operator, sometimes written as OR. In this case, we are looking at things that are in one set or are in the other set. So we're looking for elements in either set. Or either set. Either? Oh, it's either in one set or it's in the other set. Okay. We'll use this term disjoint to refer to sets that have no elements in common. So if we're looking for elements that are in one set and in the other set, and they have no elements that are in both of those sets, we say that the sets are disjoint. Okay. Now, we've encountered this next term before, complement. Okay? The complement is everything else but what you have in the set that you're interested in. So in terms of sets, it means elements in our universal set, okay, but not in the given set. So if our universal set was food and we were talking about the set fruit, okay, the complement of fruit would be all kinds of food that are not fruit, that are not in the set of fruit. The null set is just a way of saying that the set has no elements. Okay. Or it's an empty set. Okay. And often we denote the null set 0 with a slash through it. Okay. Null, nothing in there. And finally, the thing that we're going to talk about a lot is what we call a subset. And a subset is a set whose elements are all in another set. So we take one set, we take some of the stuff, or all of the stuff, from that set, and we can make another set, which is a subset of that first set. And there is a symbol that the learning guide uses that goes along with subsets. It looks kind of like this, okay? Kind of like like the intersection or the union sort of tipped on their side. This means, we read this as is contained in. Okay, so one set, a subset, can be contained inside another set. Okay. So that's some of the symbols that we'll be looking at here, and we'll do a couple of examples here just to sort of reinforce the meanings of these things. So here we've got a group of sets, okay? A, B, C, D, okay? And our set S, so our universal set, or all the things that we're interested in here, is 1, 2, 3, 4, 5, 6, 7, 8. So for the purposes of this question, those are all the numbers that exist. Okay? So the first thing it asks us to find is A intersection B. So what does this mean? It means all of the elements that are in A and are in B. So we look at set A and we look at set B and we look for things that are in both of them. Well, let's see. 3 is in A, 4 is in A, 3 is in B, 4 is in B. So the intersection of A and B is the set consisting of 3 and 4. For the next one, we want A union B, so we want all the elements that are in A or in B. Well, to do that, we're just going to list the things that are in A first, 1, 2, 3, 4. Okay? And then add in the things that are in B. Well, let's see, we've already got the 3 and the 4 from B, so we don't need to write it again. So we just add in the 5. So the set A union B is going to be 1, 2, 3, 4, 5, or A or B. Let's see, we want C union D here, so the set of things that are in C or in D. Let's see, we've got 5, 6 from C, and then let's throw in the 7 and the 8 from D. Okay, and again, we don't write those repeated elements twice. Let's see, next one, A intersection C. So all of the things that are in A and in C. Well, A has got 1, 2, 3, 4. Are any of those also in C? Nope. So we can write this, if there's nothing in the intersection of these two sets, no elements common, we can either write a set with nothing in it, okay, or we could write it as the null set. Okay? Now, what we can't do is write that. Okay? Because what that means is the set that contains the element 0. Okay? Which is not one of our things in our universal set. So you don't want to do this, you want to do this or this. Okay? Now, we can always use these, operators between two things. We can also use it sort of to do more than one operation. So here we want B and C and D here. So we want the elements that are common to B and C and are also common to set D. So let's look at these 3 sets here. What elements are in all 3 of those? There's only one of them, the element 5. So we can have sets with single elements, we can have sets with no elements. Our final one here, we want a complement. This little apostrophe means complement. So we want all of the things that are in our universal set but are not in our set A. So A is 1, 2, 3, 4. In our universal set, we also have 5, 6, 7, and 8. So 5, 6, 7, and 8 would be the complement of set A.